So in our last video, we introduced the characteristic polynomial and the characteristic equation, how to find eigenvalues. Remember, you just take the characteristic equation and solve for lambda. So what is the characteristic equation? Determinant of what? A minus lambda I, where I is your eigenvalue, equal to 0. So basically, you replace the x in the characteristic equation with the lambda to find your eigenvalue. So this is true if and only if lambda is an eigenvalue of A. Lambda is an eigenvalue of A. All right, so let's do some more practice. We'll do a problem 3. So we want to find all real eigenvalues of A. All real eigenvalues. We're not going to do any complex. So for example, if you get a complex eigenvalue, we're not going to worry about doing i's and stuff like that. All right, so here's a matrix. 3 by 3 is what? 1, negative 1, 3 down the first column. Second column's 0, 1, 0. Third column's 2, 0, 2. And we're ready to find our eigenvalue. So lambda is an eigenvalue. Precisely when, what happens? Determinant of A minus lambda I. I'll say I3. You don't have to say, you can just say I. A lot of people just say I. They drop the 3. It's understood to be a 3 by 3. Equals 0. All right, so that's going to be what? Determinant of equals 0. So we're going to subtract down the main diagonal. We're going to subtract a little lambda. We're going to have 1 minus lambda, 1 minus lambda, 2 minus lambda. Then the other entries stay the same, right? We get 0, 2, 0, negative 1, 3, 0. So we got to find the determinant of that matrix, and then we set that equal to 0, that polynomial equal to 0, and we solve for lambda. So if I were finding the determinant here, I would probably expand across the first row. We're going to have what signs? Plus, minus, plus. So I start with 1 minus lambda. And I cover up the first row and the first column and look at the determinant of the following submatrix. Determinant of, let's see, we have 1 minus lambda, 0, 0, and then 2 minus lambda. Doesn't want to write. Okay, I covered up the first row and the first column. Okay, my second entry along that first row, I don't really need, right? I just got a minus 0. So then I can go into my third entry, which is going to be plus 2 times the determinant of the following submatrix. So I'm going to cover up the third row and the first row and the third column. First row and the first column. First row and the third column. First row and the third column. I'm going to have entries negative 1, 3 down the first column. The second column, 1 minus lambda. And 0. All right, so now we're ready to the next step. Oh, and this is a set equal, I forgot, this is all equal to 0. This is going to be a polynomial equal to 0. So going on, we have what? 1 minus lambda out front. Okay, we're going to take the determinant of 1 minus lambda, 0, 0, 2 minus lambda. So you multiply down the descending diagonal. You have what? 1 minus lambda, 2 minus lambda. Minus, well, 0 times 0 is 0. That's going up the ascending diagonal. And then here it looks like we have what? Plus 2. And we're going to take the determinant of this matrix. We're going to have what? Negative 1 times 0 is 0. Minus, and then we're going to multiply up the ascending diagonal. It's going to be negative. So minus 3 times 1 minus lambda. Now that's all equal to 0. So what happens? We got 1 minus lambda in parentheses. We got 1 minus lambda in parentheses. We have 2 minus lambda in parentheses. All right, then over here, we can multiply this 2 and this negative 3 right here. That's going to give us, minus 6. And then we have in parentheses remaining 1 minus lambda. And all that's equal to 0. I just kind of ignored the 0 right here, right? That 0 you can just ignore. All right, so what do we have? Well, it looks like we got something we can factor out here. Looks like we have a 1 minus lambda in common, right? So this is equivalent to, I'm going to factor a 1 minus lambda out in common. And this is going to leave me with, in a big old bracket, this is all equal to 0, don't forget. What do we have left? 1 minus lambda, 2 minus lambda. That's not a 2, is it? It's a negative 2. 2 minus lambda, and then a minus 6. Right, we factored out that purple 1 minus lambda. All right, so this is going to be equivalent to, let's see, 1 minus lambda. And then in this bracket here, all of this is set equal to 0. Inside this bracket, we want to FOIL. Let's FOIL these blue dudes, 1 minus lambda, 2 minus lambda. So we got 1 times 2 is 2. 1 times negative lambda is negative lambda. Negative lambda times 2 is negative 2 lambda. Negative lambda times negative lambda is positive lambda squared. All this is minus 6. All right, so I'm sticking with cleaning that up. I'm going to have, 1 minus lambda. That's ugly, isn't it? Ugly. This is all equal to 0. We got to clean this up, right? We got lambda squared. Combine the lambdas, you get minus 3 lambda, right? And you combine the constants, and you get 2 and negative 6. 2 and negative 6 is negative 4. All right, so that blue stuff, I think we can probably factor that, right? So let's do another step. We have what? 1 minus lambda. We're going to factor this blue stuff. I'm going to put blue parentheses here, and this is all equal to 0. Don't forget this is all equal to 0. How do you factor that? Well, you're going to have a lambda, and then you got to find two numbers that multiply, give you negative 4, and I have to give you negative 3. I'm going to do, negative 4 and positive 1, right? Negative 4 and positive 1. They multiply to give you negative 4. That'll give you negative 3. So you have a polynomial of the degree 3, and it's factored, right? Factored, you got 3 factors. So from those 3 factors, they get set equal to 0, and they give you 3 roots here. You get lambda equals 1, lambda equals 4, or lambda equals negative 1. So these are going to be 3 distinct eigenvalues. They all have multiplicity 1, so the multiplicity of 1 is 1. The multiplicity of 4 is 1. This is called algebraic multiplicity. There's something else called geometric multiplicity that can be different. Multiplicity of negative 1 is 1. They all have multiplicity 1. They show up exactly at one time, no repeated roots. All right, so that's kind of nice, which is one problem. Let's do another. What was that? 3? So I got a 4 here somewhere. I had a 4 written down. Let's do a 4. Yeah. Here I got what? 1, 0, 0, 0, 1, 0, 0, 1, 0. No. This is wrong. This is supposed to be a 1 right here in the corner. My bad. All right, so that's our matrix. We want to find all the eigenvalues of that matrix. All right, so lambda is an eigenvalue of A. Precisely when the following happens. The determinant of A minus lambda I is equal to 0. So I'm actually going to kind of skip writing A minus lambda I. I'm going to take, down the main diagonal, I'm going to take 1 minus lambda, 1 minus lambda, and 0 minus lambda. So I subtracted lambda from the main diagonal entries. That's what you essentially do, and everything else stays the same. So eventually you get to the point where you can do this. You can think ahead. I have to show every little tiny step, right? And, oh, I keep putting a 0. I don't know why I keep putting a 0 there. It should be a 1. A 1 down in the corner. That should, come on. That should be a 1. There we go. And that should be a 1 right there. There we go. Thank you. Nope, not yet. There we go. All right, so we want to take the determinant of that. I think it's easiest to take the determinant if you expand across the first row. If you do that, you're going to have what? 1 minus lambda times the determinant of the submatrix. So you cover up the first row in the first column, you're going to have what? 1 minus lambda, 0, 1, negative lambda. And if you continue to expand across, you have what? Plus, minus, plus. If you continue to expand across that first row, those are just 0 entries, so they're not going to be consequential. So this is all you need to do for the determinant. And this is equal to 0, right? This determinant is equal to 0. All right, let's keep going. Let's take the determinant of the 2 by 2. So we got what? 1 minus lambda out front. And when we take the determinant of the 2 by 2, you multiply it on the descending diagonal. We have what? 1 minus lambda times negative lambda minus, and then you multiply up the descending. 0 times 1 is 0. And all that's equal to 0. So if you write this out, you get this is equivalent to 1 minus lambda, 1 minus lambda, negative lambda. All this is equal to 0, right? Basically that 0 doesn't matter right there. All right, so you got 3 distinct factors. It looks, no, you don't have 3 distinct factors. So you got what? A repeated factor right here. This one's repeated. This is 1 minus lambda squared. If you wanted to write that, you could write that. I'm not going to bother writing that. So this is equivalent to saying that 1, lambda equals 1, and lambda equals 0. And those are your 2 eigenvalues. You only have 2 eigenvalues. The multiplicity of 1, though, is 2. It's called algebraic multiplicity, and the multiplicity of 0 is 1. Right, 0 is only going to show up once because you only have 1 factor of negative lambda. But the eigenvalue of 1 is going to show up twice because you have the factor of 1 minus lambda 2 times. All right, let's do one more quick example, maybe not too lengthy, where we're finding these eigenvalues of matrices. Here's one, number 5. A is a matrix 1, negative 1, 0. 0, 1, 1, 0, 1, 0. And we're finding the eigenvalues. Let's do it. Lambda is an eigenvalue of A. Precisely when, that's if and only if. Determinant of A minus lambda I equals 0. So basically I'm going to take my diagonal entries, 1, 1, and 0. And I'm going to subtract lambda. I'm going to have 1 minus lambda, 1 minus lambda, negative lambda. Hey, that's looking similar to the last one. And then we got these other entries, 0, 0, 1, negative 1, 0, 1. Okay, these are a little different, I think, than last time. Let's see if we can take this determinant. Well, hey, I can expand across the first row like we did last time, right? We just got a bunch of zeros after that first entry. So I'm going to have what? 1 minus lambda. That looks a lot like last time. Times determinant of the submatrix. Submatrix, when you cover up the first row, first column. 1 minus lambda. It's not writing. There we go. 1, 1, negative lambda. This is equal to 0. But let's see if we can calculate that blue determinant there. So I got my first factor out front, 1 minus lambda. And then the blue determinant, we're going to, let's see, we're going to take these guys and multiply them down the descending diagonal, 1 minus lambda times negative lambda. And then minus, we're going to multiply these green guys up the ascending diagonal. Well, they're supposed to be green, not blue. 1 times 1, 1, right? Now this is all equal to 0. So I'm going to have what? 1 minus lambda. And now I'm going to expand my dude in the brackets. So I got to do some foiling for the red. I'm going to do what? negative lambda plus lambda squared. Right, that's the red part. So that's not FOILing, that's actually distributing, right? Negative lambda times 1 is negative lambda. Negative lambda times negative lambda times squared. And then we get a minus 1. This is equivalent to what? 1 minus lambda equals lambda squared minus lambda minus 1 equals 0. Now it turns out you can't factor this second factor very nicely. It doesn't come out very nicely with rational numbers or anything. So you actually would want to go somewhere and do some scratch work. You want to use the quadratic formula. So off to the side, I'm going to use the quadratic formula. So what was our equation? Say we want to solve that. Lambda squared minus lambda minus 1 equals 0. Lambda squared minus lambda minus 1 equals 0. So you'd have what? Lambda equals minus b. B is going to be negative 1 plus or minus the square root of b squared negative 1 squared minus 4 times a 1 times c negative 1 all over 2a, 2 times 1. Okay, so the double negative here is going to make a plus. So we're going to have 1 plus or minus the square root of. Here the negative and the negative are going to cancel. We're going to get what? 1 plus 4. And on the bottom we're going to get 2. So that implies that lambda, that's not an x, that's a lambda, equals 1 plus or minus the square root of 5 over 2. I believe one of those is the golden ratio, right? 1 plus square root of 5 over 2 is the golden ratio. So those are your roots. So you're going to get what? Lambda equals 1. Lambda equals 1 plus the square root of 5 over 2. You're going to get lambda equals 1 minus the square root of 5 over 2. And each of these has multiplicity 1. Okay, I'm just going to write that. I'm going to put a little note here, where each has multiplicity 1. Okay. All right, so I think I'm going to stop there as far as finding eigenvalues, real eigenvalues of matrices. In this video, we'll pick some of this up in another video. We'll do some, maybe some more theoretical stuff in the next video.